Hello, ENET 140 class. This is our first recording of lecture notes for operational amplifiers. Many of you are not able to make it to the live class or have other issues that prevent you from being able to participate, and we find it sometimes challenging to cover enough material in class, so this is an attempt to bridge that gap and give you a little bit of verbalization from my own notes. So this evening I'll be speaking to you about negative feedback. This material is all coming straight out of the Fiore Op Amps book, Chapter 3, and I'm going to be just talking straight from the notes that hopefully you are seeing here from my own handwritten PDF scanned notes. And this is what I lecture from live in class, and so I'll just be discussing more of that. I talked about some of this morning in class, but I'm going to go back for a recap because I think we could all do with a little bit of a refresher, and again, a lot of you weren't able to make it. So, negative feedback. For those of you who've read Fiore Chapter 3, you'll probably remember that he goes into a bit of the nitty-gritty about exactly what negative feedback is. Talking about it from a general principle of what it does to the gain of an amplifier. He defines open versus closed loop gain, defines the feedback fraction, sacrifice factor, and a lot of other things that have to do with the gain, input and output impedance, and bandwidth of an op amp that has a feedback network. Most particularly has a negative feedback network. Positive feedback is reserved pretty much for the realm of oscillators, and that comes much later in this class if we get to it at all. So we're only talking, when we talk about feedback in the context of this class, we're talking specifically about negative feedback. Okay, so the concept behind negative feedback. You add a portion of the output signal back to the input signal such that the magnitude of the differential input is reduced. And the differential input, of course, is what we were talking about with comparators, and that is the V non-inverting minus the V inverting. That is actually defined as the differential input. So if we have an input signal that we're, maybe of 1 volt that we're putting in on the non-inverting terminal and the inverting terminal is grounded, we could say that the differential input is positive 1 volt. So we're going to alter that by mixing in, quite literally, a portion of the output signal. So what's the benefit of negative feedback? It renders the op amp self-stabilizing. So this is basically like a thermostat, a temperature controller, a speed controller in the car. As your output signal rises, you're feeding back subtractively a portion of that rising signal, so the differential input is reduced and the output's reduced, and vice versa. So here is a little diagram of how that happens. We've got our operational amplifier with an open loop gain. And that means the gain it would have if the feedback network wasn't there at all. So that's big. That's that 200 to 500,000 thing, of which we use very little because we're ultimately limited by the voltage of our supply rails, which are not shown here. We have a feedback network, which could be as simple as a voltage divider or as complicated as something that would take more space than this paper. And it's labeled with a beta. This little symbol here looks like a B. That's the Greek letter beta, and that is the portion of the output signal, that is fed back over here to the input. So it's a fraction. So if we were feeding back half of it, half the output back into the input, the beta would be 0.5. If we were feeding back 25%, it would be 0.25. So this little box here, or this little pinwheel, is called a signal combiner. And so you can see it's got positive and negative selections. So if you plug a signal into the negative, it means you're subtracting, or you're adding something that's 180 degrees out of phase, which is of course the same thing. So you've got your input signal coming in that's positive, and then we're adding the portion of our output signal that is constituting our feedback into the negative, so we're subtracting it. So as you go past the signal combiner, you have a blended signal, and we call that the error signal. Not because it's erroneous, but I don't know, it's just the name. So it's V error, and that's the new input to the op amp with feedback. So it's kind of like the closed loop version of the differential voltage. So it's now what the amplifier is going to act on. So mathematically, the error signal can be defined as the input, which is coming in from outside the circuit. It's this low amplitude signal, maybe coming from a thermocouple or a pressure sensor or something like that that we're trying to amplify, minus the feedback signal, minus the feedback voltage. Okay, we can further define, well, okay, so what is that feedback signal? Well, it's the output, V out, times the fraction we're feeding back. So now we can define all of these in terms of one another, and we will use these relationships mathematically to define our closed loop gain on our closed loop versions of other important parameters like input and output impedance and bandwidth. And we'll spend a lot of this chapter deriving those relationships and then using them. Okay, little vocabulary. Closed loop. That's the term that is used to describe any kind of circuit characteristic of the op amp when feedback is present. And at least in the Fiore book, it's noted by the subscript CL for closed loop. And I think that's common to a lot of the tutorials you might find online. Sometimes the closed loop characteristic will be described by a subscript PP or SP or PS, and in that case it's still closed loop, but it's going further and actually describing the type of feedback network, whether it's a series parallel or a parallel parallel or a parallel series, and we'll actually get into how those are arranged and configured a little bit later, but those are actually just different types of ways in which to achieve negative feedback, and they would all be a closed loop condition. Open loop is the bare naked op amp with no feedback network, and that's noted by a subscript OL, and I'll tend to try to write the L kind of in a cursive in my notes. So AOL is open loop gain, and because it doesn't have a prime, it would probably be a voltage ratio, so it's the voltage out divided by the voltage in when no feedback network is present. And if we had a series parallel style feedback network, if you saw an ASP, you would know that that was the voltage ratio expression for the closed loop gain for that series parallel negative feedback equipped op amp. Okay, another very important term is called loop gain, and that's just the ratio of the gain of the op amp as a voltage ratio in the open loop condition divided by the gain as a voltage ratio in the closed loop condition. And it doesn't matter what style of feedback network, series parallel, parallel, whatever, it's basically just the open loop gain divided by the closed loop gain. And because generally speaking the closed loop gain will always be less, loop gain is always a positive number, and sometimes is a pretty big one. Another name for loop gain, a synonym, is called sacrifice factor. It's noted by a capital S. You'll see this all over the Fiore chapter 3, and it is an important benchmark parameter in the relationship between open loop and closed loop properties across the board, not just gains. Okay, so what do we get with a loop gain of greater than 1? And You can see here this is boxed in yellow. It says less than 1. It really should say greater than 1, because loop gain is pretty much always greater than 1, because our closed loop gain here is always less than our open loop. So the loop gain should be greater than 1. So what do we get by sacrificing some of that open loop gain? 1, increase midband frequency range. This is a very good thing because, as you remember from chapter 1, the midband region, frequency region of an op-amp is where its gain is stable with frequency. It's constant. We don't have to worry about how our gain is changing with frequency. So we want that range to be as big as possible. So when we sacrifice a little bit of that open loop gain, or maybe a lot of it, with a negative feedback network, we will extend that midband frequency range by sometimes several decades or more, which really increases our ability to process signals of widely different frequencies, which op-amp networks are often used for. And the other important gain that we get, haha, pun intended, is decreased distortion. And in this case, distortion has a very specific definition, and it is an unwanted voltage signal that's being generated as part of the op-amp output. So that's something that's common to many op-amp circuits. And so when we use a negative feedback network and sacrifice a little bit of gain, we will proportionately reduce that that output distortion along with our reduction in gain. And so it's important to remember that this is no big loss. Because remember, we're not making use of probably 1/10 of the total gain available in the average op-amp, because we're limited by the rail-to-rail supply voltage. So we can certainly afford to sacrifice some of that massive open loop gain and get all of this this good stability. And again, we'll go through mathematically exactly how that is a one-to-one trade for different types of negative feedback configurations. Okay, let's shift back up and take just a quick refresher of our generalized negative feedback circuit here. Notice that the default configuration is the feedback voltage signal being in phase with the input, but being subtracted, or effectively being 180 degrees out of phase. So it's essential that your V error going into the op-amp consists of an input signal and then 180 degree out of phase feedback network. So what happens if that isn't the case? Because we know from our study of leading and lagging networks that that we have coupling capacitors on our input and our output, and because we have a coupling capacitor and we have some intrinsic resistance in our circuits, we've got an RC network. And remembering back from our AC circuits, we know that when we have a real resistance and a capacitive impedance, a Z, we have a phase angle, and it's frequency dependent because our X sub C is equal to 1 over 2 pi times the frequency times the capacitance. So as we shift frequency, we shift the imaginary component of our impedance and therefore the phase angle. So if you think about it, if we have a frequency swing in our input signal, we could get to the point where our V in and our V feedback, rather than being 180 degrees out of phase, are in phase and are now positively fed back. They're constructively interfering rather than destructively. So that would be bad. We would not only lose all of the great benefits of negative feedback, we would completely destabilize the circuit and turn it into an oscillator, which those of you who are experienced with this know is terribly easy to do. There are two performance benchmarks or circuit design benchmarks that tell you how far away you are from that dangerous condition. dangerous for your circuit performance. And those are called the gain margin and the phase margin. And they basically tell you how much of a safety factor you have in keeping your negative feedback condition. So we'll start with a gain margin, and we'll look at that in terms of what gain you have at a point where the input and the feedback signals are 180 degrees apart, assuming that they're going to be subtracted. So I know this is kind of a double negative. The 180 degrees apart in this case is kind of where they would constructively interfere. So we're assuming they were 0 degrees apart and then subtracted, and that's good. That's negative feedback. So if they're 180 degrees apart and subtracted, they're actually being added. So that's not good if you want negative feedback. If the closed loop gain, though, is less than 1, even if the signals are being added, because the gain is less than 1, you're not going to get signal reinforcement. You actually have signal attenuation just because the gain is less than 1 or less than 0 decibels, negative decibels. So that's called gain margin. So if you take the circuit performance at a point when your input and your feedback signals are 180 degrees apart, where you don't want them, if you want to maintain negative feedback, and say you have, at that point, you have a gain of a closed loop gain of, say, 0.5, then you would have a gain margin of 0.5. So you'd need 0.5 to make it back up to 1. If you had the signals 180 degrees apart and the gain was more than 1, you would have positive feedback and probably go into oscillation. So now I repeated that 3 times. Okay, so the other portion of this is called phase margin. So if you assume that your gain, your closed loop gain is 1, so it's kind of right on the border. It's as high as it can be, and not go positive. How close are your input and your feedback signals to being 180 degrees apart, assuming they're being subtracted? So if your input signal was coming in with a phase angle of 120, and your feedback signal had a phase angle from the reference point of say, I don't know, 20, adding those together, you would have 140, so you would have a 40-degree phase margin, assuming that at that condition you had a closed loop gain of 1. And so those are just ways of telling you how close you are in either closed loop gain or phase, input to feedback signal, in losing your negative feedback condition. So I will, if you're still confused about this, I would highly suggest you look at our Fiore Chapter 3 textbook. He's got a couple of fabulous graphs that show this and show them all aligned and the conditions that would cause either one. But the main consideration is you need to keep that state of negative feedback, destructive interference, diminution of the output signal due to the portion of it being fed back. If you go to a state of positive feedback, all of this goes out the window and you probably oscillate. Okay, so that said, we're going to examine the 4 different flavors, you might say, of a negative feedback network and how you achieve them, why we would want one versus the other, and then we'll kind of zero in on one particular type and derive all kinds of relationships for gain and impedance for that configuration, and then take a brief look at one other. Okay, so here we have a figure of another generalized feedback network. So we have our op-amp with a certain gain, and that's its open loop gain because we haven't quite hooked a feedback network to it. These are dotted lines. And we have a feedback network with a beta. So this is the fraction of the op-amp's output signal that is going to be returned and added in or subtracted from the input. And we can hook these up in a couple of ways. We can hook them up with a series connection at the input end or a parallel connection at the input end, or we can have a series connection at the output or a parallel connection at the output. And we'll take a look at what those look like coming up. But something we need to remember about series and parallel connections in terms of how the circuits perform, remember that anytime we have a series connection, we're going to end up having a higher impedance. You've got a certain amount of resistance, real or imaginary, with any kind of component, and if you stack them up together, those impedances add. Z1 plus Z2 plus Z3 equals Z total. It's going to be bigger than either one of Z1, Z2, or Z3. It's a series addition, just like resistors. Okay, in parallel, as you know, that if you have a lot of impedances or resistors in parallel, the total resistance or the total impedance is always less than the lowest one of the ones that are added in parallel. So that gives you a very low impedance connection. So if we want something to act like a voltmeter and very faithfully transmit a voltage signal, we want a high impedance connection. So if we're going to put a voltage signal into the input end of the op-amp and we want it to be faithfully reproduced and then amplified, we'd probably want to think about having a series type connection out here. And likewise, if we want to extract a voltage signal or flow a lot of current out the output, we want low impedance, so we might want a parallel connection. And in fact, that series on the input plus parallel on the output is what works best if we're going to go for voltage gain, and that's the one that we're going to kind of use as a prototype to derive all of our closed loop gain and impedance and bandwidth relationships for a negative feedback network. So that's what we're going to use. So here it is. This is the series parallel negative feedback general configuration. So now we've fleshed our bare naked op-amp out a little bit. We're showing it with its own open loop gain, its non-inverting terminal, and its inverting terminal. So for the series parallel configuration, we put our input signal, again, it's coming from some thermocoupler, pressure sensor, photocell, or whatever. It's our signal coming in from outside the circuit. It's coming into the non-inverting terminal. We have our output voltage as usual, and so coming out, the signal coming out of the op-amp now has a parallel path. It can either go straight to the load or it can go to the feedback network, so there's a parallel choice here. We've got a feedback network. Don't know what the configuration is. Could be simple or complicated, but it's got a beta. So there's going to be a certain fraction of this output signal that's swiped and it's fed into the inverting terminal of the op-amp. And so we call the voltage at that point, that's V feedback, and it's going to be equal to the beta of the feedback network times the output voltage. So we know what the voltage is at that point. So V error, which is the difference between our non-inverting and inverting terminals with feedback, is going to be our V in minus beta times V out. That's the signal that's going to be acted on by the amplifier. And in fact, the open loop gain of the amplifier acts on that V error to give us our output signal. So that gives us a couple of equations here. So we've got V error, which is defined as the differential input to the op-amp with feedback condition. So we can see that given that this is our feedback circuit, our circuit with feedback, we've got V in minus the signal at our inverting terminal, which is beta times V out, also known as V feedback, and that V out is equal to the open loop gain times V error, which is the differential input with feedback. So we have two different equations. So we can combine these and get some other expressions. So we're going to define closed loop gain for this configuration now. So this is the ASP, meaning the voltage ratio, V out over V in, voltage gain, with in the closed loop condition using a series parallel negative feedback network. So that's our A closed loop for this configuration. It's equal to V out over V in. Okay? So we're going to algebraically eliminate V out, V in, V error, and V feedback. Because we don't necessarily know what those are if we don't measure them. We'd like to get this gain expression in terms of beta and the open loop gain, because those are the kind of things we can either define by the as fabricated circuit in the case of beta, might just be a simple voltage divider, and the open loop gain of the op amp we can look up on a spec sheet. So we want our closed loop gain in terms of something that we can see, design, or look up. So let's do some algebra. So again, we can take this expression, V error equals V in minus beta times V out, and rearrange it. So we got V in on one side, and then we're going to write V out as V feedback over beta, and we've just done some substitution there with this expression. So again, we're just doing some mathematical wrangling, and of course that's equal to this expression. So we rearrange some terms, and we get V error equaling V feedback over beta times the open loop gain. And we can do some more substitution up in this expression, factor out V feedback, and we end up with this term, which is very important. We'll see that again and again. And note that in the case where A open loop is very large, this will default to 1 over beta. But so far all we've done is some algebra. You can try to work through these steps. This is also in the Fiore textbook, or you can trust my steps. That we can end up with these two expressions for V in and V out. And oh hey, look, if you ratio them here, V feedback cancels out. So now we have our closed loop gain in the series parallel configuration ends up just being 1 over beta plus 1 over the open loop gain. And we can multiply that by the open loop gain on the top and bottom. Again, just some more algebra, and we end up with this circled expression. So this is something that you will probably want to commit to easy memory if you're doing a lot of problems or you're working through more of these derivations, because you'll see this again and again. That is the open loop gain over beta times the open loop gain plus 1 is the series parallel closed loop gain. So if you think about how big the open loop gain is, it's like, say, 250,000. And beta's not nearly that big, but it's certainly not going to be less than maybe 0.1. This 1 here gets real small in comparison to the beta times the A open loop. So you can approximate this expression by 1 over beta. Because this will be small, this one term will be small, you can discard that, and then the A open loop cancels with the A open loop, and we're left with just 1 over beta. So wow, that's pretty cool. What that tells us is that the open loop gain and the closed loop gain are related fairly simply. Let me rephrase that a little bit because I think I said something confusing. So the closed loop gain series parallel, the whole thing, I apologize here, this whole thing simplifies to just 1 over beta. The whole closed loop gain is 1 over beta. So the closed loop gain is the inverse of the feedback fraction itself. So I can have an op-amp with an open loop gain of 250,000, and if I have a feedback fraction of 10%, say 0.1, then my closed loop gain is 1 over 0.1, or just 10. I got rid of a lot of gain. I only have a closed loop gain of 10. That's pretty easy to calculate. And in most cases, that'll be enough to get me pretty close to the supply rails anyway. So I'm going to end this recording now at the top of page 5. As you can see, there's 15 more pages of notes to go through, but we have now effectively defined closed loop gain for the series parallel, most popular configuration of negative feedback op-amps, especially for voltage gain, in terms of our open loop gain and our feedback fraction. And we will use that relationship in our next recording and further in the notes to look at the effect of our series parallel closed loop negative feedback condition on bandwidth. And we'll show how we get a much bigger bandwidth, much wider midband range. So we'll end this recording now, and hopefully we'll have another one out soon.